Hi again, everyone. Again, my name is Vidergar, and I work at National Emergency Response Team called CICERT as incident responder and malware analyst. And today I'm here to talk about analysis of a very interesting malware sample we observed and quite frequently also analyzed at National CICERT called HijackLoader. This HijackLoader performs very interesting malware techniques and is also the primary reason for many Slovenians who fell victim to fake CAPTCHA scam to lose all of their crypto savings through their crypto wallet compromise. Before I start talking about the actual analysis part, I would like to talk about initial vector, which in this case is in most cases the fake CAPTCHA scam. I believe everyone here is familiar with the concept. So we are talking about malicious website essentially that just shows HTML and JavaScript code, which in the background copies the malicious PowerShell command or MS-HDA command into the user's clipboard and essentially just asks user, hey, press this combination with the keyboard, so Windows R, Control V, and Enter, to essentially execute malicious PowerShell command, which downloads malicious sample and infects the system with info-stealing malware. As far as I know, this concept first developed by famous cybersecurity YouTuber John Hammond. I believe everyone is familiar here with his name, as he runs one of the biggest cybersecurity YouTube channels out there. The actual technique, how the malware, this malicious website copies malicious PowerShell into the clipboard differs from case to case. But I decided to show only the most interesting technique I've discovered so far, and it's through the use of smart contract. Here we can see the malicious JavaScript actually connects to Binance smart chain platform, which hosts or where the smart contract is deployed and developed. Actually calls with the Web3 JavaScript library a malicious method of this smart contract, and as a result retrieves the malicious PowerShell command. I implemented the same logics using Node.js, as you can see in the PowerShell window, to essentially get this PowerShell command out of the smart contract. It's also interesting that the contents of this malicious PowerShell command that is returned by the smart contract has already changed. Last time I checked, like 3 days ago, it returned a string like goodbye or something like that. So it's interesting to see that malware authors also change the smart contract contents as well. Again, that's malicious website is not part of actual HijackLoader I'll be presenting today, but it acts as an initial vector how the malware is actually distributed and how it infects the endpoints and the actual systems. Here we can see Binance Smart Chain website. If we inspect this smart contract, we don't see the actual human readable code, but EVM bytecode. So the malware has to specify this ABI structure, application binary interface, and specify the address of smart contract and call just the right method to actually retrieve this PowerShell command. Then again, user has to run this malicious command in order to infect its system with the HijackLoader, which leads to info-stealing infection. Here, before we dive deep into each stage of HijackLoader, I decided to create a graph of infection chain, how the actual malware execution happens on the system. So there are 3 main stages. So the malicious JavaScript copies malicious PowerShell into the command, user runs it, and it effectively executes the first downloads and then executes the first stage HijackLoader binary. This first stage HijackLoader binary is responsible for overwriting parts of its text section into the P structure, overwrite it with the first stage shellcode, which extracts the image out of it, the matter of fact is this malware exe file that is downloaded by the PowerShell holds an image, an actual PNG file inside its resources, so it's a part of binary, and the malware actually extracts its pixel values to retrieve the shellcode, which is the second stage shellcode. Second stage shellcode is responsible for performing different malware techniques, like loading additional anti-DLL into memory, extracting syscall indexes, to effectively perform process hollowing, another injection technique, which leads us to stage 3 of HijackLoader, which then performs yet another kind of injection, which is based off NTFS transactions. It's called process doppelganging, just another injection technique, which then performs the final injection of passing the final info stealing payload into the remote process. So that's just a quick overview. Now we will dive deeper into each stage. So I would like, just for now, you to remember there are 3 stages of HijackLoader, and the final, actually the 4th stage is the final info stealing infection with the crypto stealing malware. That's the stage 1 binary. So the binary, the exe file that is first downloaded and run by the PowerShell command. If we just analyze it statically, we can already see it contains within its structure a P resource. That's a PNG image, which holds the encrypted second stage shellcode. You can already see this image looks kind of random. It has multiple red, blue, green pixels. It doesn't make sense as an image, but from malware point of view, this just screams about technique called steganography. It's a malware technique which essentially allows a malicious program to store a malicious payload or malicious code inside a media file, like in this case image, but it can also be a video or even music file. Like I said, first stage program is responsible for overwriting a part of its text section, overwriting it with the first stage shellcode, which is responsible for parsing this image you've seen on the previous slide. This image holds different 16-byte blocks from the malware perspective, and malware first reads these pixel values from the image, builds a linear buffer, an actual array, and then searches for valid block out of every block that are 16-byte within this image. Once it finds the valid block based on CRC32 checksum matching, it extracts XOR key, which is also contained in the valid block, and the payload size. So it can perform XOR decryption, which is the simplest encryption possible, to essentially obtain the next stage shellcode. So that was stage 1. And usually, when you have to do some kind of decryption in malware analysis, you have 2 options. Either do it statically, meaning you implement the same logics in a standalone program or mostly Python script, or you can do it dynamically. So you let the malware execute and essentially do the decryption itself. For presentation purposes, I decided to use the debugger, to use the dynamic approach, and I essentially set up a breakpoint just after the decryption loop, so after the XOR decryption happens, so those encrypted pixel values are decrypted into a memory section that now holds, as you can see, some interesting strings like that are part of malware configuration, and at the end you can also see the next stage shellcode, which is injected into the DLL in the next stage. It's also interesting to see that malware never changes this section throughout the whole execution of the program, as it's really important. That's probably the most important memory section in the memory of this process, as it holds the malware configuration it uses throughout all 3 stages, and also the stage 2 shellcode, which happens to be the same as the stage 3 shellcode. So just to sum it up, up until now. So we had fake CAPTCHA website where user effectively self-infected its system. Then we had first stage binary, which decrypted an image and built essentially a structure, and finally decrypted the second stage shellcode. It then injected it into the system-loaded DLL library. And we are now here at second stage. Second stage performs numerous different techniques. I won't have time to cover every of these techniques, but I decided to pinpoint the most interesting ones. And the first one of the stage 2 techniques that are performed by this malware is loading additional anti-DLL library. Anti-DLL is a Windows-provided system library, which is the lowest laying user mode library, and it's essentially just wrapper around syscalls. I believe everyone here is familiar with the concept. Applications run in user mode of the operating system. And in order to execute anything meaningful, really, like establishing TCP connection, writing to a file, anything useful, really, they have to communicate with the OS kernel. And they do that with the use of syscalls or system calls. Anti-DLL offers those syscalls, so the application developers don't have to know these syscall values. And the problem here is that since anti-DLL is so important for every process in the Windows, antivirus, EDR, XDR solutions like to hook it. That means if you inspect the actual disassembly code of the anti-DLL library, you will see certain jumps or certain different instructions that allow antivirus solutions to inspect the arguments to essentially determine whether application in question is malicious or not. And malware authors, of course, know about this antivirus hooks placed into the anti-DLL library. That's why they decide to load additional anti-DLL library. So what happens? This malware just straight up loads another anti-DLL, this time from disk, and doesn't rely on system-provided anti-DLL, which is hooked by the EDR solutions. How it does so? It calls different Windows APIs, like create W to essentially create a file object to obtain the handle to the anti-DLL that is in syswow64 directory, and then creates a section with low-level API called ZW create section, and then maps a view to it into memory, which just results in another copy of anti-DLL in memory, which is now without the EDR hooks. That was the first technique. And the second technique I would like to mention is the use of API hashing. Up until now, I haven't mentioned it so far, but all those APIs you could see in the code, like GDI API to extract the pixel values in stage 1, or creating a section in stage 2, the code I just showed, those APIs aren't seen by default if you check the shellcode in IDA Pro disassembler, because API hashing is in place. This means that the shellcode holds only the checksums or hashes of those related APIs, and the malware has to do some calculations, calculate every checksum of the exported function in DLL libraries, and therefore do the matching to resolve the pointers to those APIs. So that's pretty standard technique. Malware has to walk certain structures like PEB, which is process environment block, walk an export directory, but this technique is pretty standard. What is not so standard is resolution of actual syscall values. Low-level APIs, like I mentioned before, offered by anti-DLL, can be also triggered just if you know the syscall index, the actual hexadecimal value that you just load into a register and then do the syscall itself. Therefore, malware can completely avoid calling into anti-DLL low library functions to essentially perform injection techniques that we'll see in the next stages. So the whole goal is here for malware to be as hidden as possible and essentially execute without EDR solutions detecting its malicious activity. Here we can see that the malware parses the export structure of anti-DLL loaded from disk, and it actually extracts the syscall indexes that it can directly call, again, for performing process injection in the future stages. As I said, So far, I covered loading additional anti-DLL and extracting the syscalls. And malware now has two options to essentially call those low-level ZW Windows APIs to execute process injection in the following stages as stealthy as possible. So it has luxury of calling into the anti-DLL that was loaded as secondary copy, if you remember from the previous slides. And it also has an option to run the syscalls directly with the technique I just showed earlier. But to do that, malware has to go through the translation layer, as the all code we've covered so far was 32-bit, which is quite common in malware. A lot of code is still 32-bit, but in order to run on the 64-bit operating system, which is most common on modern machines, it has to go through some kind of translation layer. There is just no way for any program for any 32-bit program on 64-bit Windows to sneak past the translation layer. And there are two options. Translation layer is usually offered by the operating system, but in this case, malware also performs this translation by itself. So the second image is the assembly code of so-called Heaven's Gate translation layer, which enables malware to just put a switch and execute those direct syscalls it needs for process injection in the following stages. So the important code starts with call 33. Push 33 hexadecimal value, so it pushes the immediate value of 33 onto the stack, and then immediately after is call $+5, which just calls the next instruction, and call instruction also saves, pushes to the stack the address of the next line. In the next line, then add instruction happens, which increments this pushed value by 5, and this value now points to the address just after retf instruction. Retf instruction is just return var, which tells the malware, hey, take less 2 arguments pushed onto the stack and execute in 64-bit mode. That's essentially just a switch from 32-bit to 64-bit in order to execute those resolved APIs by syscalls. Why did the malware do all this work? So it loaded additional anti-DLL and it resolved ZW just by calling the syscall values alone. The goal is to remain as hidden as possible because antivirus solutions would quickly detect this malicious activity of creating new process, injecting into the DLL and so on. So that's why malware tries to hide malicious activities by calling low-level APIs by direct syscalls. Here we can see a code executing process hollowing, which is another injection technique. It relies on creating a new process and then after that creating a file-based memory section out of this DLL present on the disk and mapping a view of this section into the memory. After that, we can see the instruction at the top of the image, which is ZW virtual protect virtual memory, which essentially changes permissions in one of sections that is present inside the remote process of the newly loaded DLL library. This allows malware to write a shellcode, this time third stage shellcode, into the remote process, which happens to be the same as the one present in the stage 2. So the whole point of this code is to create another process, force it to load additional anti-DLL, change its permissions, and write a shellcode into it. Just another injection technique, this time a little different, and it's called process hollowing. The catch here is malware creates new process with a pipe. So even though the newly created process it's not suspended, it's waiting for the pipe. And once the malware writes into the pipe, the new process is executed. So far, we covered first and second stage. And once this injection happens of process hollowing through low-level ZW resolved API calls, we are talking about stage 3, which happens to be the same shellcode as it was in the stage 2, but it behaves completely differently as per malware configuration. And this time it implements another injection technique that's NTFS transacted hollowing, which is a combination of process doppelganging as well as the process hollowing, similar technique we've observed just from stage 2 to stage 3. Here I prepared a graph how this looks. It heavily relies on transactions, which is a concept very similar to the one we know from databases. And one of the main benefits of transactions is atomicity, meaning that two independent actions, like for instance, paying and receiving money, happen in one single action, at least from the outside. And similar concept exists in a file system, NTFS, which allow any application to essentially almost write a file onto the disk without actually writing it to a disk, but the file itself acts as if it was on the disk. So why is this important? For the whole time, this file actually stays in memory and is inaccessible to any other process, including the antivirus process. But the malware has a luxury of actually treating this file as if it was on the file system actually written on a disk. That's important because for malware, it can map it much easier and much more efficiently if it's on the disk, as it can create a section directly as an image, which is not so straightforward if it only has a copy of this malicious payload inside one of the memory sections. So malware enjoys the benefit of having this malicious payload containing info-stealing payload, essentially as if was on a disk, but it's not actually on disk and therefore is inaccessible to any other process, including the EDR solutions. How does this happen? You can see a combination of different API calls. First, malware creates a new transaction object. Then it creates a new file, new temporary file, writes malicious info-stealing payload into it, and this is the transacted file, meaning it is not actually written on a disk, but to malware it looks like it's on a disk, therefore it can create a file-based section and map it directly as an image. Then, once it creates this memory section with the malicious info-stealing payload, it can just say, you know, operating system, I was kidding, roll back this transaction. And essentially, once the NTFS transaction is cancelled, essentially with the rollback, this file is never accessible again, as if it never existed. But the malware has already included it, has already loaded it as an image into memory, into one of its sections. And from this point, malware can simply do the process hollowing, very similar technique we observed before to get from stage 2 to stage 3. The whole reason for this kind of injection is, again, to hide the malicious payload, the info stealer, and hiding it essentially from antivirus solutions, because if a process drops something on a disk, antivirus solutions quickly go check it and kill the malware process. But that's how this HijackLoader avoids the detection and killing the process. That's the code. In IDA Pro, again, I had to apply certain structures and enums. So the code is easily readable. We can see creation of transaction, creation of new temporary file, writing to it, creating a new section, and doing the transaction rollback, and after that executing the process hollowing. The final info-stealing payload is either, in most cases, it was either Luma stealer or Sectopret, two .NET info stealers that have different capabilities, but the main ones are stealing user passwords and stealing crypto wallets from the infected system. I quickly did the dynamic analysis. It's interesting to see that the C2 IP address where all the user data gets sent to threat actors is hard-coded within this binary, and it also has a fallback mechanism to find the malicious IP C2 address through pastebin. And at this time, it just points to the same IP address as is already hard-coded in the actual binary. Just to sum it up until now, we've covered fake CAPTCHA website, which was initial vector for initial infection. Then we covered 3 stages of HijackLoader. First one did the extraction from the included image within PE resources, decrypted the shellcode, injected into system-provided DLL, and then stage 2 essentially loaded additional anti-DLL, parsed syscall values in order to perform process hollowing on a very low level, and then stage 3 executed or performed process doppelganging through the use of NTFS transactions to hide the final payload and do the process hollowing into yet another, this time third process, which was infostealing malware, again targeting crypto wallets and users' password. That's it from my side.
Thank you, Urban. Are there any questions? Yeah, okay.
I have a few questions. First, when you have all this overview about statistics of security incidents in Slovenia, how well are antivirus programs doing well this after analysis, or do they find out this kind of attacks? And second is it enough to block user access to command line, PowerShell, and Windows Run? And third is, how about this to what are the consequences or impacts of this kind of attacks, especially on just focus what you had stealing passwords?
For the fake CAPTCHA, you're asking?
No, for this kind of through scripts which are in images, hidden commands.
Mm-hmm. So the image, if you're asking about PE image that was included into the PE, that's just the use of steganography. It's just one way of essentially hiding the malicious code inside the P binary. There are numerous different techniques to do that. It's also possible, like you asked, another question, to block execution of malicious PowerShell commands through the use of Windows R, Windows Run. Windows and some companies actually implement that, and it's also possible to see for users who are unaware if they accidentally ran one of those commands into the registry a certain path. You can see the history of all commands that were executed through Windows R, Windows Run command. And you had one more question, I forgot the first one.
How well are antivirus programs doing if you're doing after this analysis? Do they find out something or any
Which
results?
programs?
I don't know, Asset, Sophos, I don't know which one.
I haven't
because
tested.
You have overview about Slovenia, so.
I haven't tested every program, but based on VirusTotal results, it had very low score, meaning I believe it was around 10 when we first analyzed the sample. And around 60 antivirus solutions didn't detect the stage 1 binary as malicious.
And there was another. Yep.
Hello, thank you for the talk. I have 2 questions. One is regarding the NTDLL replacement versus just doing your own syscalls as they do. Why do they do both? The NTDLL replacement really does feel like doing your own syscalls, doesn't it?
Yeah, exactly. NTDLL is just a wrapper around syscalls. It's very simple code. I don't have a question. I don't have an answer to this question. I was also surprised to see both techniques at the same time, but it also depends on malware configuration, because those those kinds of samples are usually provided by malware developers who first build a builder, and a buyer essentially doesn't have to know anything of this. They just click what options they would like to use. And so I imagine malware developers implemented multiple different techniques, and the user or the buyer selects those it wants, but both techniques are equivalent.
Thank you. And the other question I have is regarding this create transaction NTFS stuff. Is this ever used by like real applications, or would a kernel level EDR be able to just see this as super suspicious and end you? Like,
no, it's used by legitimate applications as well. It's not so common, but you cannot rely just if the one application uses NTFS transactions, it's malicious by default. But it's definitely something antivirus solutions should look into it.
I see. Thank you.
Any more questions? If not, thank you, Urban.